I will explain you theorem 6.2.1. Here you can read the statement of this theorem. This is a very important theorem. Okay. Because this is the first theorem that you can see in section 6.2. Maybe the probability of asking this question is high. Okay. So let us read the statement. The element lambda belongs to F is a characteristic root of T belongs to A of V. Here lambda is the characteristic root of T. Okay. So T is from where? T is from A of V. If and only if for some V not equal to 0 in V, Vt is equal to lambda V. Okay. This is what? This is our if and only if statement. So first what you are doing is, let us follow my notes, okay? So that looks very better. So here I am assuming the first part, okay? By assuming this first part in the statement, I will prove this. So assume lambda belongs to F is a characteristic root of T belongs to A of V. Just copy it down from the question. Now this lambda is the characteristic root of this. So by the definition of characteristic root, you can write this lambda minus this T is singular. How you are writing? You are writing this from the definition of characteristic root. Do you want to see that? I will show you. Here, look at this. Can you see this? If T belongs to A of, this is a definition of characteristic root, okay? If T belongs to A of V, then lambda belongs to F is called a characteristic root or eigenvalue of T if this lambda minus this T is singular. Singular is also called as not regular. So here if lambda is called the characteristic root if lambda minus T is singular. So here in this statement, in our assumption we have lambda belongs to F is a characteristic root. Then you can say lambda minus T is singular, right? By the definition of characteristic root. So we have to prove this. Now we have a theorem that if V is a finite, I am writing the statement of the theorem, okay? If V is a, I am going to use this theorem in this proof, okay? So that is why I am writing that theorem here. I am mentioning that the theorem that I am going to use in this proof, okay? So if V is finite dimensional over F, then T belongs to A of V is singular. If and only if there exists V that should not be equal to 0. This V belongs to capital V such that this V into this T equal to 0. I am going to use this theorem. So here if T is singular if and only if Vt equal to 0. Here what we have? Here lambda minus T is singular. So what we have to write? The same way you are writing, okay? In the place of T, in this theorem you have T because here T is singular. In our proof, lambda minus T is singular. So in the place of T, here you put lambda minus T. Okay. So here listen. Therefore, here there exists this V not equal to 0 in V. Same sentence, okay? Such that V into, in the place of T, here T is singular in this statement. So you are putting Vt equal to 0. But in our proof, you are having lambda minus T is singular, right? So put this V and in the place of T, here you are putting lambda minus T equal to 0. Is that clear? Now, in the next step, you are just putting an adjustment. You are multiplying with, lambda is multiplied with an identity element. Identity element is 1. So even if you multiply lambda into 1, you are going to get lambda, right? So for a little bit adjustment, because you want to make this adjustment, okay? You will know about why you are making this adjustment in the further steps, okay? V into lambda I minus T equal to 0. So here you are multiplying. So you get V into lambda I minus Vt equal to 0. So here bring this lambda outside so that you will get lambda into Vi, you get Vi is V, right? So that is why lambda V minus Vt equal to 0. So bring this Vt to this side, equal to right hand side of this equal to, so that you will get lambda V is equal to Vt. This is what we have to prove, right? This is what we have to prove. You have proved. Now we are passing on to the converse part of this proof. So here you can see the converse part. We are assuming this. By assuming this, you will prove this. Lambda is a characteristic root of t. Okay. So to prove lambda is a characteristic root of t belongs to A of it is enough to prove this lambda minus t is singular, right? If you proved this, then automatically this will be proved. Okay. Now we have, in our assumption, we have Vt equal to lambda V. Now in this next step, what you are doing, you are bringing this to this side so that you will get this. Sorry, I'm so sorry. You are bringing this to this side. Okay. So you will get lambda V minus Vt equal to 0. Now lambda into in the place here, instead of V, you are putting Vi. Because value is not going to change, so that is why minus Vt equal to 0 implies V, you are bringing V outside, and lambda I you will get. It is okay, it is correct, it is okay to write lambda equal to lambda, right? That is what V into lambda minus wait a minute, V into lambda minus, you are taking V common, okay? Here is also you are having V, here is also you are having V, you are taking V outside, so that you will get in the place lambda I minus t. It is okay to write without I, right? So you are writing without I, you will get this. By the theorem we get, so from this you can say, what theorem? By a theorem means the theorem we have used here also, right? By the same theorem, right? Here you got this part. You got this part. From this you can say what? Lambda minus t is singular. Here Vt equal to 0. T is singular. Right? T is singular means Vt equal to 0. So here in the place of t you are having what? Lambda minus t. Right? So you can say by that theorem, you can say lambda minus t is singular. Am I right? So that is what you are writing. So you have proved lambda minus t is singular. So if you proved this, then automatically this will be proved, right? By the definition of what? Characteristic root. So you have proved it. So automatically this is also proved. So you proved this theorem.